Hello students, today we will study about the isomers of carbon. But before this, we will have an idea about the term isomerism and and how we can define the isomers. Basically, isomers are defined as the compounds which have same molecular formula but different in the physical and chemical properties. So, isomers can be defined as those compounds which shows same molecular formula. For example, if I have the molecular formula C4H10, by this molecular formula, for the first structure what I can write, since this compound follows the general formula of an alkane, so by this the first structure what I can write is CH3 connected with CH2. Another CH2 group is there with the terminal CH3 group. And one more structure we can write by this, that is CH3 connected with carbon single bond hydrogen. The terminal CH3 group is there, and to satisfy the valency of this carbon atom we will add a CH3 group here. Now if we talk about these two structures, then these two structures have the same number of carbon atom, that's 4, and the same number of hydrogen atom is there, that's 10. So since they have the same molecular formula, but due to the different arrangement of carbon atoms in the structure, they will be having different physical and chemical properties. Like they will be having different melting point, different boiling point, and if we talk about their chemical behavior, so they will be having different chemical reactivity to the different reactants. Now, according to the above definition what I have given, these are the compounds which have the same molecular formula but the properties of them are different. So these two compounds according to the above definition can be termed as isomers, and the phenomena due to which these compounds are having different isomers, this phenomena is termed as isomerism. So this is what this is the phenomena what we will deal in this part today. But now, before we see the isomerism in organic chemistry, first of all, we will discuss the types of isomerism. Since it's a very broad term, it deals with a large number of compounds. So before we study the compounds which shows isomerism, for the conveniency, we will study the different types of isomerism. So broadly, we will see the classification of these isomers, and isomers are basically divided in two categories. The very first category is known as structural isomers, while the second category is known as stereoisomers. Now in this segment we will deal with the structural isomers since it's a very common phenomena for the carbon compound, and later on we will be discussing the stereoisomers in organic chemistry. Now these structural isomers are further classified in different categories, and the very first category what we will study here is the chain isomer. The second category is known as position isomer. In the third category, we will deal with those isomers which are defined as functional group isomers. In the fourth part of this, we will deal with metamers. And the last category for this one is tautomers. Now, we will see the structural isomers in carbon and its compound. Basically, before we see the types of structural isomers, first we are to see that what is the definition for structural isomers. Structural isomers are defined as those compounds which have the same molecular formula but they have the different arrangement of atoms, and since they have the different arrangement, so they show the difference in their structure. So now finally we can define the structural isomers as those compounds which show same molecular formula but the different in their structural formula or different in their structure. Now this different in their structure may be due to the presence of different number of carbon atoms in parent chain or in branch chain. This difference may also arise due to the presence of different functional group present in the compound. So due to which reason this difference is going to be arise. According to that, these structural isomers are further classified in different categories. And the very first category with which we will deal here is chain isomers. These are isomers, so they must have same molecular formula, and if they have the different number of carbon atoms in their parent chain or in the branch chain, then these are defined as chain isomers. For example, if the molecular formula is given to us and the molecular formula is C5H12, since the molecular formula follows the general formula of alkene, then by this molecular formula we can write the one structure like this one. The another possible structure by this molecular formula is, now if we follow about these two structure, then these two structure has the same molecular formula C5H12. But if I go for the selection of parent chain for these two structure, then in the very first example I will have a parent chain which is straight in nature, and total number of carbon atoms in this parent chain are 5. For the second one, if I select the parent chain with maximum number of carbon atom, then this chain will be again straight chain, but now this time the number of carbon atoms are 4. So in these two structure, the difference is due to the presence of different number of carbon atoms, and according to definition, since they are differ in the number of carbon atoms in the parent chain, so these two can be termed as chain isomers to each other. Since these chain isomers have the different number of carbon atoms in parent chain, or we may also say that they have the different skeleton structure of carbon atoms, so these chain isomers are also known as skeleton isomers. Or the another name what we use for these chain isomers is nuclear isomers. Same as what the example what we have seen in the very starting was the C4H10. If I write the structure for C4H10, then the one possibility is CH3 connected with CH2, another group is CH2 with a terminal CH3 group, and the another structure which is possible for this one. Now if we select the parent chain for these two, then for the first one the number of carbon atoms in the parent chain are 4, while for the second one number of carbon atoms in the parent chain are 3. They follow the same molecular formula. The formula is C4H10. The difference in the number of carbon atoms. So these two can also be termed as chain isomers. Now we will see the second part of these isomers, that's position isomers. Position isomers are defined as those compound which shows same molecular formula, but these isomers have the different position of functional group, or there may be the different position of multiple bond, or these may differ in the position of substituents. Now anyone out of these three, if they have the different position, then these kinds of isomers are known as position isomers. For example, if the molecular formula of any alkene is given to me, such as the molecular formula is C4H8. Now by this molecular formula, the very first structure what I can write is CH2 connected with double bond with a CH group. Now the last part is ethyl group, CH2 connected with a terminal CH3 group. The another structure with this molecular formula that we can write is CH3 connected with CH group, and now this time the double bond is in the middle. The another group is CH with a terminal CH3 group. Now for these two structure, if we count the total number of carbon atoms in the parent chain, so the number of carbon atoms are 4 in the both cases, but the difference is in the position of multiple bond. In the very first structure, the position of multiple bond is at the very first position, while in the second structure, if we do the numbering for this parent chain, so this multiple bond will occupy the second position. And these two types of structure which have the different in the position of multiple bond can be termed as position isomers. Now just now we have seen the different position of multiple bond. Now we will take an example where the different position of functional group will exist. So for the functional group, if I take the example of any alcohol with the molecular formula C4H10O, then since this is the general formula of alcohol, this compound follows the general formula of an alcohol, and by this if I write the structural formula of an alcohol, so the very first structure may be CH3 CH2 connected with CH2 group, and the terminal CH2 group is connected with alcoholic functional group OH. The another structure which is possible for this one is CH3 CH2 connected with CH group and a terminal CH3 group is there. And now this time the alcoholic functional group is present at the middle carbon atom. For these two structures, the number of carbon atoms in the parent chain are same, but the difference is in the first structure, the alcohol OH functional group is connected to the first carbon atom, while in the second structure, this alcoholic functional group is connected to the second carbon atom. So these two structures have the different position of functional group, and the different position of functional group can also be counted as the position isomers. So these two are again the example of position isomer. And the another name of compound that is given to us is 1,2-dichloroethene. So as the name is indicating, in the very first structure, this chlorine substituent is present at the first position, while in the second name, these chlorine substituent are present at the first and second position respectively. So since they are having different position, or we can also confirm this by making this structure for these compound, 1,1-dichloroethene can be written as CH2 connected with carbon atom with 2 chlorine group as the substituent on this carbon atom, and this 1,2-dichloroethene can be written as CH connected with CH by a double bond and 2 chlorine atoms each on every carbon atom. These two structures have the different position of substituent. Here both the substituent are connected to first carbon atom, while in this the both substituent are connected to different carbon atom and have the different position. And these two structures, since it has the different position, so these two can also be taken as the example of position isomers. Now we will see the third category of these structural isomers, that is functional group isomers. Functional group isomers are defined as those isomers which have different functional group present in them. And since they are the isomers, so the very first condition that's quite obvious, since they are isomers, so they should have same molecular formula. So if we are having two different structures which have same molecular formula but different functional group, then these isomers or these structures, whether they have the same number of carbon atoms or different number of carbon atoms in the parent chain, whether they have the same position of functional group or the different position of a functional group, but these will be defined as the functional group isomers. For example, if the molecular formula is given to us as C2H6O, then as this molecular formula follows the general formula of an alcohol, so the very first structure what we can write with the given formula is CH3 connected with CH2 group with a OH group on this carbon atom. Now by this molecular formula, the one functional group we can also write, this is the functional group ether. If I arrange these atoms in a way like CH3 connected with oxygen atom, and the next valency of oxygen is satisfied by a methyl group on the terminal end. Now these two structure has the same molecular formula, that is C2H6O, but these two have the different functional group present in them. In the very first structure, the functional group is alcoholic functional group, while in the second structure the functional group is ether. And since they have the different functional group present in them, so these two can be defined as functional group isomers. Now if we discuss some more examples for these functional group isomers, and now this time the molecular formula for an acid is given to us. The molecular formula is C2H4O2. Now by this molecular formula, since it follows the general formula of an acid, the one structure what we can write is ethanoic acid, CH3COOH. And if I arrange these atoms in a way like hydrogen is connected with carbon atom with a multiple bond with oxygen, and a terminal methoxy group is present. Now in the very first structure the functional group is carboxylic acid, while in the second structure the functional group is ester, and they have the same molecular formula but the functional group is different. So these two can also be termed as functional group isomers. Now we will take one more example for this. That's two general example. We all know the general formula of an alkene, and if I write a molecular formula of an alkene with 4 carbon atom, then the molecular formula will be C4H8. With this molecular formula, I can write the structural formula of an alkene, and if I write it as 1 butene, then the structural formula will be CH connected with a terminal CH2 group. Alkenes and cycloalkenes, they follow the same general formula. So by this given molecular formula, we can also write the structural formula of a cycloalkane, which should contain 4 carbon atom. And now this time the structure will be CH2 connected with CH2 group, and they will form a cyclic structure with a CH2 group, and the last one is also CH2 group, which can also be written with the square form at the 4 carbon atoms at the 4 corner end. These two structures have the same molecular formula, and the molecular formula is C4H8, but the difference is in the presence of functional group. In the first structure, the functional group is multiple bond containing alkene, while in the second structure, the functional group is cycloalkene. So since these two structures have the different functional group, so these two can be termed as functional group isomers. Now finally, we can conclude this that those compounds which follows the same general formula will show the functional group isomers. Alkene will always show functional group isomerism with cycloalkene. Since they both follows the same general formula, and the general formula is CnH2n. Same as if the general formula I write as CnH2n minus 2, then this general formula is followed by alkyne and alkadiene, and also this formula is represented by cycloalkenes. So these three will always show functional group isomerism if a molecular formula is given in the form of, if the molecular formula is given which follows the rule CnH2n minus 2, then by this molecular formula we can arrange this in the form of alkyne, alkadiene and cycloalkene, and these three structures will be termed as a functional group isomers at that time. Same as if the general formula is followed by the molecule, and the general formula is CnH2n plus 2O, then this general formula is followed by two kinds of functional group, and the functional groups are alcohol and ether. So always these alcohols and ether will show functional group isomers, functional group isomerism. Same as CnH2nO, this general formula is followed by three kinds of functional groups, that is aldehyde, the another one is ketone, and the third one is oxirane. So these three will always show functional group isomers. If with the help of molecular formula I can write the structure of any aldehyde, then it's confirmed that by this molecular formula we can also arrange this in the form of ketone and oxirane, and these three structures will be termed as functional group isomers at that time. Same as the last category for this is acid and ester. They will always show functional group isomerism because they always show the same, because they always follow the same molecular formula, and the molecular formula followed by these functional group is CnH2nO2. So these compounds will show functional group isomers. Later on we will be discussing about the fourth and fifth category of structural isomers, that is metamerism and tautomerism.